Good morning, class. Today we are going to look at relationships between variables. And studying relationships between variables is very, very crucial. One, it enables us to estimate and then exercise control given the variables you're interested in. And then secondly, having a knowledge on relationships between variables, it can be used to identify corrective measures when a system deviates from the expected. So we all know that sometimes there is need to do prediction in management, in management of so many things, in businesses, in our homes, and even countrywide. So you find that understanding relationships between variables will guide you on very good decision making, or while making key decisions in your businesses, in your homes, and even in a country as a whole. Say you're a policy maker or you're a government official, and you want to make a decision regarding certain issues. So regression and correlation is very, very important in helping us to identify how variables are related and how strong is this relationship. So correlation and regression is normally used when the data you have collected from the field is quantitative. Is quantitative in nature. But however, we also have a measure that we call the Spearman's rank correlation that we shall look at later on in this topic. They can also be useful in qualitative analysis. So let's begin with correlation. Correlation is a statistical technique used to determine the degree to which two variables are related. So the difference, before I continue, the difference between correlation and regression, I want to be brief as possible. Correlation is used to measure the degree, is used to estimate the strength, is used to estimate the extent to which the variables are related. It gives you a degree to which the variables you're looking at are related. And yet, regression only describes the relationship. It shows you how the relationship is. It shows you how the variables are related. And correlation will measure the strength of that relationship. Before identifying the correlation or using correlation and regression analysis, we normally do what we call a scatter diagram. We normally plot what we call a scatter diagram. A scatter diagram, or you can say a scatter plot, is a graph in which each plotted point represents an observed pair of values for the variables. In this case, we need the y-axis and the x-axis. As you can see, we have a y-axis and we have an x-axis. What you're seeing down here is what we call a scatter plot. That's what we call a scatter plot. The form of a scatter plot can be linear or it can be curvilinear. So a scatter plot, these are some of the things that we need to know when we are to use a scatter plot or a scatter diagram. It is a rectangular coordinate, and then two quantitative variables should be plotted, and then one variable is called the independent, and that's the x you see, and then the second is the dependent, and that is the y you see. The x variable, that is the variable you're interested in, or you can manipulate, you can play with to see changes in the dependent variable. The dependent variable is the one the person, could be a manager, could be a researcher, that you're interested in understanding. You're interested in seeing the change. That's what we call the dependent variables. So the points are not joined. The points are not joined after. So that's what we call a scatter diagram. No frequency table is required in this case. We have an example. We have an example of weight and blood pressure. So these were variables that were collected data on. So data was collected on weight and data was collected on blood pressure. Maybe this person was trying to understand the relationship between weight and blood pressure, the extent to which these two variables are related. So a scatter diagram was plotted. Blood pressure on the y-axis and weight on the x-axis. And when you look at the scatter diagram, it is not joined. The points are just scattered. They're just showing you certain a certain direction on which certain direction in which these coordinates are moving. So this is what we call a scatter diagram. That is how it looks like. You plot a variable on y-axis and the variable on x-axis, and then you begin plotting those coordinates. And then after that, you come with a scatter diagram. You don't have to join it with any line. You leave it as it is. This one, we shall look at it later on. It's called the line of regression, or the least squares regression line. We shall look at it in regression. Scatter plots. The pattern of data is indicative of the type of relationship between two variables. So after you have plotted your scatter diagram or your scatter plot, you will realize that those coordinates that you have plotted, they have a particular pattern they are following. It could be a positive pattern, a negative pattern, or a no pattern at all, whereby it doesn't shows you any pattern, whether it's positive or negative. So it could give you three different versions: the positive relationship, the negative relationship, and no relationship. So this is how a positive relationship would look like. So assuming we plotted final grade, we were looking at the relationship between final grades in the course and the number of hours spent reading. Maybe this was a research carried out by one of the researchers, and he was interested in understanding the relationship between final grade in the course and the number of hours someone spends reading. Now, assuming your scatter plot came out like that, the way these coordinates are moving, you will realize that this is a positive relationship. A positive relationship can also be known as a direct relationship. It means that these two variables move in the same direction. They move in the same direction. So your computation of the correlation coefficient will give you a positive answer, or will give you a positive error, as we shall see later on in our. So this is still another example of a positive scatter diagram. So whereby you're seeing the coordinates are moving in the positive direction. That's an example where we have height plotted an edge. So this was interested in studying the relationship between height and age of certain people. Then a negative relationship looks like that. So you're looking at reliability and age of car. So then when it was plotted, when the coordinates were plotted, you see that they gave you a negative pattern. A negative is also known as indirect relationship, or it can be known as an inverse relationship, meaning that the variables move in opposite direction. When one increases, the other one will decrease, hence a negative relationship. So on plotting such variables on a scatter diagram, you will find that the pattern of the pattern is a negative pattern. This is an example of no relationship at all. So assuming that this researcher was interested in plotting weight against the pulse rate, so the beats, you find that they don't have any relationship. And so after plotting, you find that the coordinates are scattered everywhere. They don't show you a positive or a negative, they're just scattered. So that means that you have no relationship. So on computing your correlation coefficient, you'll find that the value you get will be 0. So when your R is equal to 0, we automatically conclude that there was no relationship between the variables given. Correlation coefficient. Correlation coefficient is a statistic that shows the degree of relation between two variables. It is a correlation, it is a statistic, and normally it is denoted by R, a small r. There could be very many correlation coefficients that we can use, but the most commonly used correlation coefficient is what we call Pearson's correlation or product moment correlation coefficient. This is the one that is widely and mostly used, maybe because it's easier to calculate and easier to interpret. So the Pearson's correlation coefficient or the product moment correlation coefficient is a statistic that is commonly used to measure the nature and strength of two variables, most especially quantitative variables. So the sign of R denotes the nature of association, while the value of R denotes the strength of association. So the sign of R, the sign before the R, denotes the nature of association, while the value of R denotes the strength of association between the variables. If the sign is positive, this means the relation is direct, as I had told you earlier on. An increase in one variable is associated with an increase in another variable, and a decrease in one variable is associated with a decrease in another variable. So which means that the variables move in the same direction. When one increases, the other one will increase. When one decreases, the other one will decrease. So on computation of your correlation coefficient, you will find that the value will get, R will be positive. You will get a positive value, and that is what we call a positive relationship or a direct relationship between variables. While if the sign is negative, this means an inverse or an indirect relationship, which means an increase in one variable is associated with a decrease in another variable. They move in opposite direction. When one increases, the other one will decrease. When one decreases, the other one will increase. Hence, a negative relationship can be called an indirect or an inverse relationship. So when you're computing your R or your correlation coefficient, you will find that R will give you a negative value. It will give you a negative value, and this denotes an indirect or an inverse relationship between the variables in question. So this is the interpretation. This helps you in interpreting your results after you have finished computing your R. So the value of R ranges between -1 and +1. The value of R denotes the strength of the association as illustrated by the following diagram. So you see we have strong, we have intermediate, we have weak. And then we have weak, we have intermediate, we have strong. So as you approach this side, you're approaching to perfect correlation, perfect positive correlation. And then as you approach this other side, you're approaching to perfect negative correlation. What do I mean? If you get your R as equal to -1, -1, that will mean a perfect negative correlation between the variables in question. Then if you get answers ranging between maybe 0.75 and then maybe 0.5, that will give you an intermediate, and then a negative 0.25 and then below, that will give you a weak negative a weak negative correlation between the variables in question. And then this other side, getting 0.25, positive 0.25 is a weak, and below 0.25 and below is a weak positive correlation between two variables. And then between 0.25 to 0.75, that is an intermediate positive correlation between two variables. If you happen to get R is equal to +1, that is perfect positive correlation. So 0, as we said earlier, means no correlation. So the values of R range from -1 to +1. So when you're giving your interpretation, you will use words like strong, intermediate, weak. So if you get positive 1, that is perfect positive correlation. Let me say you get 0.95, that is strong positive correlation. If you get positive 0.30 or 3, that is weak positive correlation. So that is how we do the interpretation for correlation analysis, or for correlation coefficient, after you have computed your R. So if R is equal to 0, this means no association or correlation between two variables. So which means that those two variables do not have any relationship. One does not affect the other. There is no effect between those two variables once your correlation coefficient R is 0. How to compute the simple correlation coefficient R? This gives us the formula. So R is equal to that formula you're seeing there, the sum of xy minus the sum of x times the sum of y divided by n. N is the sample size that you're looking at. So how many observations are you looking at? So this is n. And then divided by the square root, of the sum of x squared minus the sum of x squared, the sum of x, then you square that value, divided by n, and then the sum of y squared minus the sum of y squared divided by n. So this is easier if you have already simplified all these values table, as you see, as you will see later on. This is an example of a sample of 6 children, which was taken to compare age in years and then weight in kilograms. So this person was interested in understanding the relationship between age and weight. So is there any relationship between age and weight? How strong is it? To what extent is this relationship strong? So this is the example. So if we are to get the correlation coefficient table, we shall need a table, and this is the table that will guide us in computing the correlation coefficient. Because remember, you will need the values for x, you'll need the values for y, you will need xy. Xy is the product of x and y, so which means you multiply every observation of x and observation of y, and then you get the product. And then x squared is carrying the observation x, and then y squared is carrying the observations of y. And those, we are interested in the totals or the summations of these variables. So if you're seeing here, we have the sum of x is 41, the sum of y is 66, the sum of the product of x and y is 461, and the sum of x squared is 291, and the sum of y squared is 742. So these are the values that we use in a computation of R, of the correlation coefficient. We just get these values down here and we substitute them into our correlation coefficient formula. We substitute those values into this formula, and then after we have finished the calculations, you will find that the answer they got was R is equal to 0.75, which is you can say an intermediate positive correlation between age and weight. So there is a positive intermediate relationship between age and weight. So the extent to which age and weight are related, we are saying that is positive. It is positive. It is 0.759, which is an intermediate relationship according to the diagram we used in, or you can say a strong, it will also be correct, a strong direct relationship, or a strong positive relationship, or an intermediate direct relationship, or a very strong, okay, no, not very strong, but strong and intermediate will be the best words in this case. So relationship between anxiety and test scores This is also another example that was given. And then when they computed the error, the correlation coefficient, error was given as negative 0.94, which can be interpreted as a strong negative correlation between those two variables in question. So giving error as negative 0.94 automatically shows you that there is a very strong negative relationship. When one increases, the other one will decrease. So an indirect strong correlation, or a negative strong correlation that you can do the interpretation. Then another correlation coefficient that is normally important, most especially if you have some qualitative variables in your study, or if you have qualitative and quantitative, but ranks involved, we use what we call the Spearman's rank correlation coefficient. The Spearman's rank correlation coefficient. It is denoted as RS. It's noted as RS. So these are some of the conditions under which Spearman's rank correlation is applied. It is a non-parametric measure of correlation. Correlation and the difference between correlation coefficient R, which is Spearman's or Pearson's correlation coefficient, and Spearman's correlation coefficient, is one is parametric and the other is non-parametric. I'll repeat that. The difference between Spearman's rank correlation coefficient and Pearson's correlation coefficient is one is parametric and the other is non-parametric. So Spearman's rank correlation coefficient is non-parametric measure of correlation because it involves data collected on variables in form of ranks. If you have ordinarily collected variables, then you have non-parametric measure of correlation, and that is the Spearman's rank correlation. And then if you have purely quantitative variables, so we have a parametric measure, and that is Pearson's correlation coefficient. So this procedure makes use of two sets of ranks that may be assigned to the sample values of x and y. Then Spearman's rank correlation coefficient can be computed if both variables are quantitative but ranked, and then secondly, both variables are qualitative, and that is ordinal in nature. However, it can also be computed if one variable is quantitative and the other one is qualitative. It can still be computed. So the rank the values of x from 1 to n, where n is the number of pairs of x, or values of x and y in sample. Now this is a procedure of computing Spearman's rank correlation. You have to first rank the values of x and the values of y in ascending order, and then after ranking you find the difference between those ranks, and then later on you substitute into the formula, and that gives you the Spearman's rank correlation. So we use the following, this formula. We use this formula: RS is equal to 1 minus 6 the sum of di squared. This is the difference between the ranks, and then you divide by n into brackets n squared minus 1, where n is the sample size. The value of RS denotes the magnitude and nature of association, giving the same interpretation as simple error. So the way we interpreted correlation coefficient error is the same way we interpret Spearman's rank correlation RS. The interpretation does not change. You either have a positive or a negative or a no relationship, and then it can be strong, it can be intermediate, it can be weak. Weak, strong, and intermediate, either negative or positive or no correlation at all. The interpretation is the same for both RS and R. RS is Spearman's rank correlation, and R is Pearson's or product moment correlation coefficient. This is an example of Spearman's correlation, whereby they wanted to find the relationship between the level of education X and income Y. So when you look at level of education, this is ordinally ranked, or these are ordinal variables: preparatory, primary, university, secondary, illiterate. I mean, these are ordinal variables. And then you see income is a quantitative variables. So you assign ranks to each and every one of these by arranging them, and then later on you find the difference. You're going to see in the table, you find the difference DI between those ranks, and then you square the difference, those differences, and that will give you the summation of DI squared, which you use in your formula, and get the answer for Spearman's rank correlation. So in this case, we got it as a negative 0.1, which is a weak negative correlation. A weak negative correlation. So there is an indirect or weak. You can say indirect, or you can say negative. But I told you indirect and negative mean the same thing when it comes to interpretation of correlation. Just like direct and positive mean same thing. So you could either use the word indirect, or you can use the word inverse, or you can use the word negative. So negative or indirect or inverse weak correlation between the level of education and income. That is what the comment would look. So this was just an exercise that you can try out later on, and see whether you can perfect your interpretation of correlation coefficients after you've finished computing your answers. Now we are going to look at regression analysis. Regression analysis is another technique that provides us with a version of understanding how the variables are related. Regression technique is concerned with predicting some variables by knowing others. It helps in prediction, the process of predicting variable Y using variable X. What regression is all about. So uses a variable X to predict some outcome, or variable Y tells you how values in Y change as a function of changes in values of. So correlation and regression. Correlation describes the strength of a linear relationship between two variables. I want you to pick the word describes the strength. Those words are very important. Describes the strength. Linear means a straight line. Hope you all know about that. Yet regression tells us how to draw the straight line described by regression. So now this is why I told you earlier on what we call the line of best fit, or you can say the line of least squares sum of deviations. So this is the line. It's normally gotten after you've had your scatter plot ready, and then you use the x bar and the y bar to determine where that line passes. It gives you the difference between the observations, the deviations between these observations that you have plotted on a scatter plot, or how close are they to the line of best fit. The regression line makes the sum of squares of the residues smaller than any other line. when looking at regression, when looking at regression, there are certain things we are interested in. Mm? We are interested in finding A and B. What is A and what is B? A and B, they're the ones that make up that line, the line of best fit, or the line, the least squares, regression line. However, before we plot it, sometimes it's inevitable to calculate the constants, or the called constants A and B, to help us determine how that line is, or where it will pass. Now, when you look at A, how do we get A? A is the intercept, we all know. A is the intercept in our straight line. A is the intercept, and B is known as the slope. So how do we get A and how do we get B? A can be easily gotten because you just have to subtract maybe the y bar minus the x bar and then get the A. But then B, you apply this formula down here, and then you're able to get B. Now this formula looks big, but after you have drawn your table, for simplicity, you just get the values and use them in this formula. Makes the work, and that the work simpler. So that is a regression line. So we have an intercept and we have a slope. So linear regressions, or linear equations, sorry, we have y hat is equal to A plus B plus bx. Y hat is the predicted line. The predicted line. This y hat means prediction. It means prediction. It means that this line is going to be used for prediction. So this is the slope. Changing y over changing x. This is the slope. And then this is what we call an intercept. That we call an intercept. So A is equal to y. Y minus intercept. That is an intercept. So how studying, hours studying, and then grades. So looking at this scatter diagram that we had earlier on of final grades, and then the number of spent studying, plotting a scatter diagram, and then later on identifying where the line of best fit passes. You find that we had r squared as 0.88, and then you see we have a line there of 59.98 plus 3.17. So this helps you in that line helps you in prediction. So predicted final grade in class is equal to 59.95 plus 3.17 times the hours of study. So this is helping us to do a prediction, in the final grade given the number of hours someone spends reading or spends studying. So someone who studies for 12 hours, it means that where x is, you now replace x with 12 and then find the answer. So you find the final grade, it will be 97.99 after computing the line. So this is the line that you're using for prediction. And then remember we have the y variable, which is predicted final grade in class, and then we have the x variable, which is hours of study, and then we have the constants A and the constants B. This constant A is the intercept, and then this constant B is what we call the slope. That we call the slope. The slope just measures the percentage change in y due to change in x, and then the intercept measures the value of y when x is equal to 0. That's what the intercept measures. So substituting for the hours of study in predicting the final grade, we just have to bring in the 12 hours, and then we multiply with the slope, and that will give us the final grade, the final new grade. That's how it's done. Someone who studies for 1 hour, it means you're going to substitute where there is x, you substitute for for 1, and that will give you the answer. That's what I did here. So the slope times 1, which is x. So remember, x is the hours spent reading, and then final grade is our dependent variable, or our y. However, you should be very careful at the sign before your slope. The sign before your slope is very, very important, because normally it gives you a description. It is, if it's a negative, it means a negative relationship. If it's a positive, it means a positive relationship. So you must look at the sign very well. The sign before your slope, it is very, very important in describing the relationship between variables. The sign before the slope b. Okay, that is an example. We have an example here. We are looking at age and weight, relationship between age and weight. So you need this table for simplification of your formula. So once you have the table and you have the values well calculated, you're interested in the totalities down here, that the sum of x, the sum of y, the sum of the product of x and y, the sum of x squared, and the sum of y squared, because later on they're the ones that you're going to substitute in your formula, and then you're able to get the constants a and b. So we have the constant a, we have the constant b, and the constant b is given as 0.9992 after substituting into our formula. This is just the mean. X bar is the mean. So you have the sum of x divided by n, and then the y bar, the sum of y divided by n, and that gives us 11 for y bar, and then 6.83 for x bar. And this normally guides us in getting a. You want to get the a is equal to y bar minus, as we saw earlier on. So how do we get a? That is the intercept. The intercept is gotten from the line. So you will find that you just have to first get b. You get the b, and then later on it guides you on getting the a. So b is equal to 0.92, and when you look at this, this is not a correlation coefficient. This is just a constant, but I'm interested in the sign before this constant, this slope. I told you the slope measures the extent to which y changes due to change in x. So in this case, you're seeing 0.92, but it is a positive, so which means there is a positive relationship between age and weight. But this sign here guides us also in describing the prediction line, the prediction line in which it will move, in which it will look. So when you look at y hat, so our prediction line will be 4.675 plus 0.92x. So 4.675 is the intercept, and then 0.92x, 0.92 is the b, and then this x is the independent variable. So this y is the dependent variable, and then x is an independent variable. If you want to do prediction, so we just have to replace the value of x with what we're trying to predict, and then we are able to get the answer. So in this case, you will find that we're looking at age 8.5. We're trying to predict how the weight of this person, of who is 8.5. So we use the prediction line, and then we multiplied 0.92 times 85, and then we added the intercept, and that gave us 12.50 kilograms. So we create a regression line by plotting two estimated values of y against the x component, then extending the line right and left. So this is another example that we can go through. However, This one requires us to find the correlation between age and blood pressure using simple and Spearman's correlation coefficients, and then we comment. And then later on, find the regression line, regression equation. I told you, for us to find the regression equation, mathematically, it requires us to first compute the constants A and B, and then we are able to find the prediction line that we later on use for prediction. So the last one requires us to find the predicted blood pressure for a man aging 25 years. So this is an example that we are working on. So you draw a table to simplify your calculation, just to simplify your calculation, because I told you that the summations at the end are very they're the ones that we normally use in the computations. So we pick out all these summations and then we apply our computation, as we shall see later on. So we calculate constant B, and then and this is how we calculate constant B, and then you get the answer. This is the answer for B, and then you also compute A, as I told you. For you to compute the intercept A, you will need to first find x bar and y bar. X bar is the mean of x, and then y bar is the mean of y. So that is dividing the sum of y divided by the sample size, and the sum of x divided by the sample size. That should give you x bar and y bar, which later on you use in computing the intercept A, and that guides you to writing your full predicted or prediction line. So this is our prediction line. Y hat is equal to 112.13 plus 0.4547x. So this is the slope B, and this is the independent variable x, and this is the dependent variable y. This is the intercept in our. So if you want to predict to predict x, we just substitute 25 for x, and then we multiply, and then this is what was done here. For the person who is age 25, what will be the blood pressure? The blood pressure will be 123.5. So multiple regression analysis is a straightforward extension of simple regression analysis, which allows more than one even variable. Now, multiple regression looks at you looking at more than one independent variable. Take an example. If you're looking at a relationship between education and income, the level of education and income, you will find that income is not only affected by the level of education. Income could be affected by so many other things. Take an example, your marital status. Are you married or single? It could be your qualification, your skills, your location, your geographical location. So many things could determine how much you're going to get as an income. But by looking at only education, how it affects income, you're looking at a simple linear regression. If you decide to look at more than one independent variable to determine your income, we are saying that you're looking at multiple regression. So multiple regression, this is where you look at more than one independent variable. So in this case, you're looking at marital status, you're looking at maybe skills, you're looking at qualification, you're looking at so many other things affecting the level of income, other than only looking at the level of education affecting the level of income you get as a person. Thank you for listening.